Hello students, today I am going to discuss one of the topic related to deadlocks, in which there are different handling techniques are used to handle the deadlock state of the system. There are three different techniques that can be used to handle deadlock. First is the deadlock prevention. Second, deadlock avoidance, and third, deadlock detection and recovery. In deadlock prevention, we ensure or system ensure that one of the necessary condition for the occurrence of deadlock cannot occur. In second handling technique, that is deadlock avoidance, the system ensure that the allocation of new resource request may not lead to unsafe state or deadlock state that leads to deadlock state. Whereas in deadlock detection and recovery, we ensure that our system allocates the resources as and when requested by processes, and after some time interval, a deadlock detection algorithm is executed, and if deadlock detected, then recovery task may be initiated by the system. So there are three different techniques to handle deadlock. Now, I am coming to today's topic, that is banker's algorithm. This is one of the algorithm to compute safe sequence or safe state of the system. This comes under deadlock avoidance handling strategy. Now the issues related to banker's algorithm are as follows. The name banker's algorithm was selected because this algorithm could be used in banking system to ensure that bank never allocated cash or money in such a way that it could no longer satisfy the needs of all the customers. So, on the basis of logic used in banking system, the name banker's algorithm is used. Now, in this algorithm, we compute a safe sequence that leads to safe state of the system. A state of a system is safe if the system can allocate resources to each process in some order and still avoid a deadlock. In other words, a system is in safe state only if there exists a safe sequence. Now, what is safe sequence? A safe sequence or sequence of a process P1, P2, P3 up to Pn is a safe sequence for a current allocation state if for each Pi, process Pi, the resource request that Pi can still make in future can be satisfied by the current available resources with the resources held by all processes Pj where j is less than I. When a new process arrives in the system, then that newly arrived process is required to declare the maximum quantity of each resource. This quantity may not exceed the total number of resources in the system. Okay. When a process after some time of their execution requests a set of resources, the system must check whether the allocation of these resources will lead to safe state of the system. If the system will safe, the resources are allocated to the processes requested process. Otherwise, process must wait until release of resources by other processes. This is the next issue. Now, several data structures are used. In this Banker's algorithm, several arrays or matrices are used to implement Banker's algorithm. The first one is the available matrix. This is of length m that indicates the number of instances of each resource available in the system the resource numbered from 1 to m, that is resource R1 to Rm. Second matrix used is max of n cross m. N is the number of processes, it represents processes, and m represents resources. This matrix represents the maximum demand of each process. Max of I of j equals to k means a process Pi wants or need at most k instances of resource Rj. Here is the k, the number of instances required at most. The third matrix used is allocation matrix, that is of again n cross m matrix. This represents the instances of each resource currently allocated to each process. Allocation of I of j equals to k means the process Pi is allocated k instances of resource Rj. This is the third matrix used in this algorithm. And the next one is the need matrix. It is also of n cross m matrix. This represents the remaining need of each process in the system. Need of I of j equals to k means process Pi need k instances of Rj in near future, resource Rj in near future. So, need can be computed using the formula need of I of j equals to max of I of j minus allocation I of j. In this banker's algorithm, one notation is used or may be established to simplify the overall representation. Let x and y be the two vectors of length n. Then here x is less than equals to y if and only if x of I is less than y of I. For all I 1, 2 up to n. It means if x is a vector and y is also a vector of length n, then this is the vector comparison by which we establish a notation that if all elements of x is less than all elements of y respectively, then we can say that x is less than y. For example, here x equals to 2, 8, 4, 3 and y is a vector of length 4 with element value 1, 4, 3, 2. Then here in this comparison, all element value of y is less than all element value of x respectively place wise. So in this case y is less than equals to x holds. Now in this algorithm, each row in matrix allocation and need may be treated as or referred as allocation I and need I. The vector allocation I specifies the resources currently allocated to process Pi, and the vector need I represents the additional resources that process Pi may still request to complete its task. There are two parts of banker's algorithm, or we can say in two steps banker's algorithm can be described. In first step, an safety algorithm is used to determine whether or not a system is in safe state, and after that a resource request algorithm is used to determine if requests can be safely granted. So, I am describing first the safety algorithm for computation of or determination of safe state of the system, that is existence of safe sequence. In this algorithm there are various steps. In step 1, consider work and finish be vectors of length m and n respectively. We assume there are two vectors, new vectors, work and finish, with length m and length n. Now, we initialize work equals to available, means whatever the state of the available is initialized to work vector, and finish of I for all I is initialized to false, initialized with false for all I equals to 0 to n minus 1. This is the step number 1. In step 2, now we find an I, that is a row, such that both finish of I equals to false for particular row, finish of I value is false, and need of I is less than equals to work. If no such I exists, then go to step 4. Now in step 3, if such an I is found, then we go to step 3, where a work is added with allocation of I, that is that particular row which is found earlier in step 2, that row is added to work vector, and for finish of I is now updated to true. That is, we assume that for a process Pi, the work is completed if all the required resources may be given using available matrix, that is initialized to work, and we assume after completion of the task of process Pi, it releases all the allocated resource. So allocation I is now added to work matrix, which maintain the overall available resources in the system. Now, if such an I exists, then finish of I is updated to true, and we again go to step 2 for next process. And by this we found all the processes or all such rows for which need I equals to false and finish of I equals to false and need of I is less than equals to work. And for that row we update accordingly using step 3. And after some time, if no such I exists, then we proceed to step 4. In step 4, we search or evaluate the finish vector, and if finish of I equals to true for all I, then system is in a safe state. If no any of the finish of I equals to false, then it represents the system is not in safe state, that is in unsafe state. So step 4 is the final step, in which if finish of I equals to true for all I, then system is in safe state. This algorithm require order of m cross n square operations to determine whether system is safe or not. In second part of Banker's algorithm, another algorithm is used named resource request algorithm. This is used to determine if the request can be safely granted or not. Now for this algorithm, let request I be the request vector for process Pi. That is, if request I of j equals to k, then it means process Pi wants k instances of resource Rj. When a process Pi made a request for resource, following actions are taken. Some actions are taken which are as follows. Step 1. If request I is less than equals to need I, then we can move to step 2. Otherwise, an error message is generated for access demand by the process Pi. In step 2, if request I is less than equals to available, then go to step 3. In this step, we can move to step 3. Otherwise, Pi must wait because resource is not available. In step 3, the system pretend or assume that requested resource have allocated to process Pi by modifying the available matrix available equals to available minus request I, allocation of I equals to allocation of I plus request I, that is the request made by a process Pi is added to allocation I, that row of process Pi, and need I equals to need I minus request I. Means it is presumed or pretend that the requested resource are already allocated to process, so we temporarily change the state, or we assume the state change by this modification. If the resulting resource allocation state is safe, means again we have to use the safety algorithm to compute the safe state, and if the safe state found, then Pi is allocated the required resources, otherwise Pi must wait and state is restored to previous state. This is all about Banker's algorithm.